In this video, I want to talk about non-terminating systems. Before I start the discussion, I want to ask you guys to please open model 7.1, the model that we developed in previous session. That's the one in which we learned the concept of sequence. Please open that model. That's the model that we are going to use to learn more about the concept of non-terminating systems and how potentially we have to run these type of simulation models. Okay, so please open the model 7.1, and so let's see what is a non-terminating system. So non-terminating system, as opposed to the terminating system, do not need to have a specific initial condition. So a manufacturing system is a good example of a non-terminating systems. When we in each day, a manufacturing system doesn't start from a very specific condition. They start basically from where they left off the day before. Also, at the end of each day, they don't need to necessarily stop at the specific with a specific condition. They, for example, stop after 8 hours or 10 hours of operation. They don't need to make sure that all the parts that are in the system already are done and they're leaving the system. They just close after 8 hours or 10 hours of operation, and they come back tomorrow and they just continue from where they left off the day before. So this is basically the definition of non-terminating systems. And as I said, manufacturing setups are good examples of non-terminating system. So if, for example, if I tell you that this manufacturing setting in which the parts arrive, and then after the parts come to the system, we realize, okay, they are either part type 1 or 2 or 3, and then they go through the cells, manufacturing cells 1, 2, 3, 4 in some orders, and then when they are done, they leave the system. Okay, so this is a good example of a manufacturing setting. So if I tell you that this manufacturing setting works for 10 hours each day, and I want you guys to simulate this for 2 days, for day 2, you don't need to repeat everything and start again from 0 parts in the system and just continue till 10 hours and then stop the simulation. So if you continue the simulation model, so if you run the simulation model for 10 hours, you can simply continue running the simulation for another 10 hours. The second 10 hours basically captures the second day of your manufacturing process, because as I said, in the second day, you just continue from where you left off the day before. So in the simulation environment, you don't need to stop the model. You can just continue the model running for another 10 hours. That would be your day 2. You can let the model continues running for another 10 hours. That would be your day 3. So if, for example, in this scenario, I let the simulation run for 50 hours, that is equivalent to running or letting this manufacturing facility to work for the whole week, assuming that each day is 10 hours of work and the week has 5 working days. So in that scenario, if I just run the simulation model to work for 50 hours continuously, that basically captures 1 working week of these manufacturing settings. So this is basically the definition of non-terminating system. And as you can see, compared to the terminating system, there is no specific initial condition, there is no specific end conditions for this system. So now the question is that if we want to analyze this type of system, how should we run them? For example, if I ask you that, tell me, for example, if I want to run this simulation model, let's say for a month, tell me what is the average working process in a month. Tell me what is the utilization of these manufacturing cells and so forth. So if tell me how much the part 1 or part 2 or part 3 can be produced in a month. So if I ask you this type of questions, you can't just let the simulation model run. For example, if I want to run this for a month, we can say that, okay, given the fact that each week is 50 hours, I'm going to run the simulation for 200 hours. And that will show me that will capture the manufacturing facility in a month, 200 hours. And then at the end I will report the numbers for that 200 hours, and those are the answers to what happens in these manufacturing settings in a month. That is not going to work, because that's similar to the terminating system. That's just one example of what has happened in these manufacturing settings for 1 month, right? So if you want to answer my question, you potentially have to be able to observe this system in more than 1 month. So let's say observe the system in month of January, February, March, April, and May, let's say, and then after observing what happens in this manufacturing settings over 5 months, after that you can look at the average of the reported numbers across all these 5 months, and then report those as what is happening in these manufacturing setups in each month, right? Okay, so that can guarantee that you take more samples of what happens in these manufacturing settings in each month, and then at the end you report their average. So, and obviously similar to the terminating systems, we can use the concept of replications to address that need for taking more samples that represent what happens in these manufacturing setups in each month. However, there's one more issue. The issue is that if I want to run these simulations, let's say for 200 hours, each one of them representing 1 month, and I want to run this for 5 replications. In each replication, the manufacturing setup is going to start with 0 parts in the system, right? And then again, it continues till finally the 200 hours of simulation is over. However, this is not the case in the real world. In each month, the number of parts that are already in the system when we start looking at the manufacturing setting in that month exactly depends on how the previous month was finished, or how the last day of the previous month was finished. And that basically sets up the stage for the initial condition for the next month. However, in the simulation world, if I just want to run the simulation model for 5 replications, each one of them 200 hours, each replication starts with 0 parts in the system, and that is not representing what happens in the real world. So we want to see how we can deal with this situation. And this is very relevant to modeling manufacturing setups, because if we look at the manufacturing setup in the real world, yes, in the very first couple of days when this manufacturing facility started, there was no part in the system, and gradually the parts arrived, and the working process increased, and the utilizations increased, and so forth. However, over time, when this manufacturing facility continued working, we may not observe those scenarios where there was nothing and no part at all in the system. So those situations related to this first couple of days or initial months, let's say, of this manufacturing facility happened just at the very first couple of weeks when this manufacturing setting started working. They never happened again during the life of this manufacturing setting. So basically, this manufacturing settings continues working and gradually reach to a steady state situation, to an equilibrium situation, where the number of parts that we may see on the manufacturing settings, the utilizations that we may see from these manufacturing cells and so forth, they basically they basically represent the situation in this manufacturing setting as it's working every day. And this is what we call as a steady state situation, as equilibrium situation. So we want to be able to observe a manufacturing setting in those steady state, in those equilibrium scenarios. And then in those scenarios, I can tell you, okay, what is the working process in this system? What is utilization of these machines? What is the average waiting times in the queues and so forth? So I have to put those first couple of weeks when things still had not reached a steady state in this manufacturing setting, I want to put those days aside, and I don't want to include them in my calculations. So let's see how we can do that in the simulation environment. So to be able to do that, first let's go first save your model as a new model in the folder for week 13. And name it as model 71 dash terminating system. Okay, so save it as a new model in the folder for week 13, and for the name, keep it as model 71 dash terminating systems. And in this model, I want you guys to add one more thing. I want you to please go to the statistics data module, and here double click. I want to create a new statistics, and in this new statistics I want to calculate the working process of this manufacturing setting, because I want to basically let this simulation run over time, and I want to look at the behavior of the working process over time, and then see how this working process has changed over time compared to the early days of this manufacturing setups. So this is going to be the total working process, and it's obviously going to be a time persistent statistics. And let's go to the build expression, and here the entities that I have, I want to look at number in process. So if you look at advanced, if you open the basic process variables and then open the entity, and then here you see I have the option number in process. That's basically work in process. If I click here, that brings the entities work in process WIP, and here I can give the name of the entities that I have. So if you remember, initially the parts were the ones that came to the system, but then in the simulation they were transferred into part 1, part 2, and part 3 entities. So I want to look at the working process of part 1, working process for part 2, plus working process for part 3. So if I can calculate the working process for these 3 entities and add them together, that basically gives me the working process for the whole system with respect to all the entities that are in the system. Okay. So I'm going to use this formula to calculate the working process in this system. So press OK, and don't change anything else. I also want to save this data, to save this outcome in a data file. And the reason is that later I want to use this data file to develop a plot of the working process. So I'm going to just do that in the file. I'm going to call it as total working process.dat. Okay, so that's going to be the data file in which I'm going to save the result of this simulation model. Then let's go to run. And let's assume I want to run the simulation model for 200 hours and just one replication. So that's what we want to do. So then let's run the simulation model for 200 hours. So in this 200 hours of the simulation run, about 902 entities got processed and left the system. And if I look at the working process here, I see that the working process is about 13 parts. So this is the number of parts that are already in the system. I want you guys to open your output analyzer. And when you open the output analyzer, I'm going to go to the graph menu, plot. And here, basically, I'm going to use that data file that was generated right now, the data file related to working process, to develop a plot of the working process in this 200 hours of simulation. So we pick plot, and here I have to pick the data file, add, and then click on the browse. And here I'm going to pick the total working process data file. I'm not going to change the replication because I just ran the model for one replication. So I keep it as is. And then here for the title, I'm going to put, for example, working process over time. The x-axis is time, the y-axis is going to be work in process, and I press OK. So this is basically how the working process in this system has behaved in this 200 hours of simulation. So the horizontal axis is in minutes. So that's the numbers that you see basically are in minutes. And then, as you can see, the working process has started from 0, and then gradually it has gone up, and then it has stayed around this one, and then here at some point it has gone up again. But then here again, it has stayed around this number, which is about, I think, 13 or 14, and so forth. So what we want to do here is that, as you can see, the numbers that we see here at the very start has not happened later in this manufacturing setup, right? So I do not want to include these numbers in my calculations. So to report the working process, that number that we saw when we look at the report, 13 point something, that number basically has been calculated as the average of all these data points, obviously a weighted average where the time is the weighting factor. So that's why we pick the time persistent as a type of statistics that we want to generate. However, we do not want to include these numbers in the calculations because these numbers happen just once at the very start of the work of this manufacturing setup when there was absolutely nothing in this manufacturing system. But as you can see, they never were repeated again. So what we see, for example, around these parts are representing the steady state or the equilibrium situation in these manufacturing setups, or what happens in these manufacturing setups. So if I want to provide an estimate of the working process, I have to look at these numbers, and I should not include these initial numbers in my calculation. So the question is that how I can drop these numbers from the calculations in the simulation. And there is a name for basically this period that I don't want to include in the calculation, and that's called a warm-up period in the simulation. This period, which happens only at the start of the simulation, when we assume manufacturing facility starts from 0 part in the facility, this time period is called warm-up period, and then, as you can see, after this period is gradually over, then gradually the manufacturing facility reaches to a steady state scenario or equilibrium scenario. And for as long as we run the manufacturing facility, this is what we see, and we may not observe this part anymore. How to know how long is a warm-up period? Usually this can be done by just eyes, by looking at some of the graphs that are important for us. For example, working process is a good one that can help us to get a sense of the warm-up process in a manufacturing setting. So here, for example, if I look at this setup, I can see that maybe around 2,000 or 3,000 minutes is a good time for the warm-up, because remember the unit, the time unit for the horizontal axis is minute. And here is about 200, is about 2,000, 3,000 minutes. So I can consider that, for example, as my warm-up time. So I can tell the simulation to run the simulation for 3,000 minutes, let's say, run the simulation for 3,000 minutes, and then drop this from the calculations. Do not include the numbers associated with this period in any of the statistics or outcomes of the simulation. Then continue running the simulation again for this amount of time or longer, and then start counting what happens in the system from this point. So basically the simulation consider this point as the initial condition of the system, and then it starts collecting the statistics and data related to this system from this point forward. So then I have a warm-up period that I have to specify for the simulation, and then I also have a simulation run that I have to specify. And then the simulation, as I said, will get up everything that has been collected during the warm-up and will not include them in the calculations. So let's go back to the simulation again. So here on the run setup window, I want to tell the simulation that consider some time as the warm-up period. This is something we had never specified before up to this point. So I want to specify about 3,000 minutes, let's say, for the warm-up time. We can specify 3,000, let's say. Let me do that. So I want to specify 3,000 minutes. So I can either say 3,000 minutes, or I can say that, for example, 50 hours. Both of them work. So I can say 3,000 minutes or 50 hours as warm-up time, and then run the simulation, let's say, for another 150 hours to report the statistics and everything that I expect to be calculated. So, and then again, I'm going to run the simulation. And obviously here, the simulation run is only 150 hours, right? We put 50 hours of the simulation run for the warm-up period. So that's why the number of products that exited the system has decreased. And if I go here and look at working process, you see that the working process in the first scenario was about 13 point something, and now it has increased to about 15 parts. And obviously this is because I got rid of everything that was collected in the first 50 hours or 3,000 minutes. And when these numbers that were smaller, 0, or these numbers that were smaller were dropped from the working process calculations, the average that was reported at the end for the working process increased from 13 to about 15 points. So if I want to report the working process in this manufacturing setting, this is a more reliable number than the one that we came up with initially. And obviously, like any other simulation, we do not want to look at the performance of this system only for one replication. So I want to, for example, to be able to run this simulation for 10 replications or more. And then in each replications, the simulation starts from 0 parts in the system. The simulation will run first for 50 hours. That's the warm-up period. We'll get rid of everything that has been collected for the first 50 hours, and then consider the state of the system at hour 50 as the initial condition in the system, and it's going to run the simulation for another 150 hours. So all the statistics and everything start from hour 150 to collect data. And then that's going to be repeated for 10 replications. And at the end, what I get after running this simulation is what I want to report, for example, as what happens in these manufacturing settings in terms of the working process, in terms of utilizations, and so forth. So then if you go back to the working process again, you see that this is the average across all these 10 replications, and this is the size of the half of the confidence interval that you can use to report. And this method for running the non-terminating simulation models is called truncated replications. The reason is that basically by defining the warm-up time, we basically truncate each one of the replications. This method can be a problem if the simulation is very complex and running the simulation takes time. So then let's say I want to run the simulation for 50 replications, and for each replications I want to, let's say, drop 100 hours or so for the warm-up time. So that's a lot of simulation time that I use, but it's going to be basically wasted because those are just warm-up times and I'm going to get rid of them. If the simulation is very big and very complex and it takes time to run the simulation, running the simulation for all these warm-up times for all these replications is going to be a lot of time and a lot of waste of time, basically. So then the question is that what we can do in those scenarios. So if the situations like that happen, we can just run the simulation for very long amount of time. So for example, here, instead of running the simulation for 10 replications, I'm going to just run it for one replication, but I'm going to run the simulation a little longer. So let's say instead of 150 hours, I'm going to run the simulation for 1,500 hours. Okay, so just one replication, and I'm going to pick the first 50 hours as the warm-up period. I have to do that always in the non-terminating systems. We always need a warm-up period. So I'm going to consider the first 50 hours as a warm-up period, and then I'm going to let the simulation to run for a lot longer time. In this scenario, I get a lot more data from this long simulation run. However, the only wasted simulation time that I have is just one 50 hours of warm-up, because I'm going to run this only for one replication, not 10 or 20 replication. Run the simulation again. Okay, so obviously since we ran the simulation for such a long time, the total exit is higher. However, let me go back to the working process. So this is the working process that I have observed. And what I want you guys to pay attention to is that here, there is also half width. And there is half width for all, basically everything that we have reported in the simulation. Even if I look at the entities, there is half width for waiting times and so forth. And this is a bit surprising because I ran the simulation only for one replication. If you remember, when we run the simulation only for one replications for the half width, we usually get the word insufficient because that's just one replication. That's just one number for each one of these metrics that we are interested to report. So putting half width doesn't make sense. So what happens in this scenario is that we let the simulation to run, and then we pick the first 50 hours as the warm-up time, and then they let the simulation to run for longer periods. In this scenario, 1,500 hours. So what happens what the arena does is that this arena is going to break these simulation time into some intervals, and it's going to look at what happens in each interval separately. And basically each one of these intervals are going to be considered as one replication, similar to that. And the advantage of this method is that since, for example, the second interval starts from this point, which is the end of the first interval, as if I already have gotten rid of the warm-up period. So this point in the manufacturing setting is definitely a steady state setup. Okay, so I don't need to worry about the warm-up period. Then for the third interval, the simulation starts everything from this point. And this one definitely is in the steady state. So I don't need to worry about the warm-up and so forth. And the same for the fourth interval and so forth. So the start condition for each one of these intervals is actually representing the steady state of this system. So I don't need to worry about the warm-up period for each one of them. I only need to do the warm-up once and get rid of it. And the rest of these intervals are good. And I can look at the data for each one of them as one replications that for which I have also gotten rid of the warm-up time. And then at the end, the simulation reports, let's say, the average across all these intervals. And this method is what we call as batching in a single run. Okay? So basically, that's the second method for running non-terminating systems. And the first method that I told you, as we just talked about it, was the truncated replications. And as I said, the truncated replication method is good if the simulation is not too complex and it doesn't take that much to run it. Then we can put the warm-up time in each replication. That's good. However, if it takes time to run the simulation, we don't want to put the warm-up time in each replication. We can just get rid of the warm-up period for once and run the simulation for a longer time, and then the simulation itself will divide this longer time into smaller intervals. We call it batch intervals, and then report the average across each one of these intervals. We have no control over the size of these batches or size of these intervals. What happens in the simulation is that when the simulation is long enough so that the arena can make sure that these intervals are basically independent from each other, then the arena generates 20 intervals, and report the numbers across those intervals. However, if we continue running the simulation longer, the arena is going to combine, for example, the interval 1 and interval 2, and then consider that as one bigger interval and use that in the calculations and so forth. So the only thing, sometimes if we do not run the simulation long enough, still when we look at the confidence, the half-width column, we may see that the word insufficient written in the half-width column. That means the simulation was not run long enough so that the arena can make sure that all these intervals that it has come up with are independent from each other, so that it can trust on averaging the results of these intervals and so forth to develop a confidence interval. However, if we continue running the simulation longer, at some point, arena can do the calculations and make sure that these intervals are independent from each other and report the confidence interval for us.